Welcome to session 9, when we look at TCP/IP protocol suite and IP addressing. At the end of the session, you should be able to know the 4 layers of the TCP/IP model, describe the functions of each layer, compare the OSI model with the TCP/IP model, understand why subnetting is necessary, explain the difference between public and private addressing, and understand the functions of reserved IP addresses. There are a number of topics that we want to cover. Key topics, introduction to TCP/IP, internet addresses, how to obtain an IP address. The reading list is shown on the slide. The OSI reference model. The OSI reference model is mostly an architecture blueprint that networking and computer device manufacturers should implement. The model is designed in 7 functional layers, and we have seen that earlier on. The open system interconnection model makes it easy to visualize the mechanisms that enable communication across networks. Upper layers use the services provided by the lower layers, but the internal workings of each layer is not visible to the other layers. This is a diagram of the OSI model. And so at the very bottom, you have the physical layer. On top of it is the data link layer, and then the network layer, transport layer. This forms the data flow layers. And then the session presentation application layer forms the application layers, are referred to as the application layers. The layer 7, the application layer. This layer represents various network applications such as email, web browsers, hypertext, file transfer protocol, etc. The application layer provides a user interface and processes network data. The application layer has protocols that are used to exchange data between programs running on source and destination hosts. The application layer on the sending host produces the network data that needs to be transmitted to the sender host. The application layer on the receiving host consumes the network data produced and transmitted by the sender host. There are 6 processes involved in the OSI model where the application layer begins and ends these processes. The diagram here shows you pictorially what happens when what happens at the application layer and how that information is then transferred down the other layers. So something is done at the application level, and then that information is then transferred down the other layers and then back to the application layer at the receiving end. The presentation layer is mostly concerned with data format. It converts the data between different formats so that both the sender and the receiver can use heterogeneous data. Recall that people may be working on different machines and therefore different systems. So it is important that this information is sort of made similar, that they can understand each other. The presentation layer on the sending host receives the data payload from the application layer. So the payload comes from the application layer, and then converts that data into a format that is easily transportable over the network. The presentation layer on the receiving host then converts the data from the network format back to its native format. The session layer. Some applications need to open logical communications channels between the computer hosts. So that's the logical communication channels, or what is known as sessions. They need to maintain data about the communications established between the network applications running on the sending host and the network application running on the receiving host. It handles authentication, because some network applications use authentication mechanisms before they can open a logical communication channel with a remote host. So you can think of instances where the session layer is important. The transport layer manages the transport of data between two hosts over a network, slices the data to be transmitted into small chunks called data segments that can be easily sent over network medium. The transport layer is responsible to reassemble the data in order on the receiving host as well. So this data is segmented, is put into data segments, sent over the medium, and then the transport layer on the receiving host then reassembles this in the order in which it should be. The network layer is responsible for routing data packets across networks that links the sending and the receiving host. It chooses the best route to send the packets between the hosts. It assigns logical addresses to all the devices in the network to be able to identify each source host and each destination host. It receives each data segment from the transport layer on the sending host, wraps it in a data packet along with the routing data. The layer 2 transmits the data on the physical medium. The data link layer receives each packet from the network layer on the sending host, wraps it in a data frame along with the local routing data. The data link layer sends each data frame down to the physical layer to code an electrical or optical signal to transmit the data frame over a wire or over the air. On the receiving host, the data link layer unwraps the data frame received to extract the data packet and then sends it up to the network layer. The network layer then sends it up again to the layer above it, which is the session layer. Then the layer 1, which is the physical layer, provides the electrical, optical, or over-the-air connections between the sending host and the receiving host. The physical layer is also responsible for defining the procedural and functional standards to enable transmission of data link frames. These standards define how a physical link is built, activated, maintained, and deactivated to enable transmissions between the data terminal equipment and the data communications equipment. Recall what the data terminal equipments are and what the data communications equipments are. Now, so we have looked at the OSI model. Let's turn our attention to our TCP/IP protocol suite. This was commissioned by the US Department of Defense, who created this as a reference model because they needed a network that could survive under any conditions. Some of the layers in the TCP/IP model have the same name as the layers in the OSI model. The protocol suite is shown in this diagram. It consists of 4 layers: application layer, transport layer, internet layer, and the network access layer. The application layer in the TCP/IP model is responsible for handling high-level protocols, issues of representation, encoding, and dialog control. So the TCP/IP protocol suite combines all application-related issues into one layer and ensures this data is properly packaged before passing it on to the next layer. Telnet, for example, will provide capability to remotely access another computer, FTP to download or upload files, hypertext transfer protocol works with the World Wide Web, and so on. Under the transport layer, there are 5 basic services that are offered. It's responsible for segmenting upper layer application data, establishing end-to-end operations, sending segments from one end host to another end host, ensuring data reliability, and providing flow control. So the diagram shows you what happens at the transport layer. You have the 2 basic things: the transmission control protocol, the TCP, and the user data protocol are resident or are under the transport layer. What about the internet layer? What does it do? Its purpose is to send packets from a network node and have them arrive at the destination node independent of the path that is taken. The protocols that are associated with the internet layer are the IP protocol, the ICMP, ARP, and the RARP protocols. The network layer, or the network access layer, is concerned with all of the issues that an IP packet requires to actually make what? A physical link to the network media. This includes the WAN and LAN and WAN technology details and all details concerned in the OSI physical and data link layers. So it sort of combines the issues and the physical and data link layers into that area. So under there, under network access layer, that you find, Ethernet. I mean, okay, this diagram shows you the internet layer and the protocols that are associated with it. Now, what are the similarities between OSI and TCP IP? Well, you can say that both of them have application layers, though they include different services. Both have comparable transport and network layers. They are packet switch, not circuit switch technologies assumed. As a networking professional, you need to understand and know both models. What are the differences then? TCP/IP combines the presentation and session layer into its application layer. So it combines the two layers in the OSI model into one layer. The TCP/IP also combines the OSI data link and physical layers into one layer. The TCP/IP appears simpler because it has fewer layers. Other than that, it does practically the same functions. The TCP/IP transport layer using UDP does not always guarantee reliable delivery of packets, as the transport layer in the OSI model does. So let's look at the internet architecture. Any two computers anywhere in the world following certain hardware, software, and protocol specifications can communicate reliably even when not directly connected. That's the basic nature of it. LANs are no longer scalable beyond a certain number of stations or geographic separation. You cannot scale them. Internet addresses. An IP address is a 32-bit sequence of ones and zeros. To make the IP address easier to use, the address is usually written as a 4 decimal numbers separated by periods or dots. This way of writing the address is called the dotted decimal format, and we had mentioned this previously in earlier sessions. The diagram shows an example of an IP address as a 32-bit binary number. If you look at that diagram carefully, you see using our distance that you can actually convert these things now, because that one there is 2 to the power of 7, and that's 2 to the power of 6. These ones, because they are zeros here, they will end up as 0, so all you have to do is add this value to that value, you get the number, a required number. So 2 to the power of 7 is 128 plus 64, that gives you 172, which is that number there. So instead of, of course, you can see that it's much easier to remember 172 than to remember this number here. And then if you look at the other octet, that, again, you can try to convert it, 2 to the power of 3, and then 2 to the power of 1. All the rest will give you what? Zeros in them. And then the next octet, again, is only the 2 to the power of 5, which is 32. That will give you a value. The rest would what? Result in zeros, and so on. So it's easier, of course, to what? Remember this type of number than to remember this number. And recall also that we said that a certain number of bits is reserved as for the network address, and the rest as a host address. So in this case, you can see that 172, the first 16 bits is used for the network, and the next 16 bits is used for the host. So if you did the binary to decimal conversion for that number, for example, then the result will be what 192.57.30.234. This is for this binary number. If you did the conversion into a decimal conversion and converted it into a dotted decimal form, you can see, like I've said earlier on, that this is far, far easier to understand than that number. Now, how do you get this? Recall, this is the the eighth position, which is 2 to the power of 7 plus 2 to the power of 6. Add that and verify that you achieve this number, you get this number. And then this one, this is 2 to the power of, this is in the third position. So 2 to the power of 5 plus 2 to the power of 4 plus 2 to the power of 3, and then plus 2 to the power of 0. Yeah? If you add that, you can verify that that gives you 57, and so on. IP address classes. We did mention that IP addresses, the network addresses, have classes depending upon the number of bits that you reserve for the network and the ones that you reserve for the host. In class A addresses, the first 8 bits are reserved for the network. In class B addresses, the first 16 bits are used for the network address. And in class C address, the first 24 bits are used for the, network, and the last 8 are used for the host. So the N stands for the network, and the H stands for the host. Now, you can tell from here straight away that in certain classes, you can have more networks and less hosts. And in others, you have more hosts and fewer networks. So it all depends on the type of network you are trying to design, whether you need more networks or more hosts. So this diagram here shows you diagrammatically what we have been talking about. So in class A, the first 8 is for the network, then the rest 24 bits are for the host. Class B, 16 for the network, 16 for the host. Class C, 24 for the network, and 8 bits for the host. Now, how does this all work out? What you then observe is that in class A, you can have, normally, that is a network, and these are the hosts, yeah? So there are 24 bits that are used for that. Now, the first two bits are actually not used. So you actually have only 16 that is left, 14 that is left, and 16 in this area. Again, in class B, if you have a 1 and a 0 here, then the network number is here. This one gives you the network number, and this one gives the host number. And the same applies for class C. Now, once you know the number of bits that has been reserved for the hosts and the network, then you can easily calculate the total number that will be on the network. So in a class A, there are 24 bits for the host. So that gives you 2 to the power of what? 24. Yeah? But then, because 2 of these things are not used, they are reserved for special purpose, yeah? For broadcasts and then for loopbacks. Yeah. So the maximum number of hosts you can get will be 16 million and so on. You can see the number there. 16,777,214 maximum number of hosts. For a class B, there are 16 bits. So 2 to the power of 16, then minus 2 to the power of 2, because, like I said, one of them is used for broadcast, the other for loopback. So you can get a maximum of what? 65,534 hosts. And then class C, because 8 bits are used, 2 to the power of 8 minus 2, which gives you what? 254 hosts. So class A addresses will normally start off with a 0. The binary range is from 000, those zeros, to 0 and then all ones. A class B address starts with a 10, and the binary range you can see. A class C address starts off with 110. A class D address starts off with what? 1110, and so on. So the table actually shows you the classes, the addresses, how they start, the range of addresses, and then the range of the decimal values that they occupy. It also tells you the maximum number of subnets that you can have on these networks, and the maximum number of hosts under each circumstance, and then the masks, the subnet mask that you will require for routing purposes. This table is quite useful because, like I've been saying earlier on, the number of bits that you use will determine the number of hosts that you can have. So if you have a certain class of network, you can only have a certain maximum number of hosts, for example. You can't go beyond that. And therefore, you have to rethink how you actually design that network if you need more than that. An IP address such as 176.10.0.0 has all binary zeros in the host portion, and therefore that is reserved for the network address. So the host section has all zeros, and that tells you that that's the network address. Now, an IP address such as 176.10.555.555 has all binary ones in the host portion, which means that it's a broadcast address. So if you have all ones in the host section, it just simply tells you that that's a broadcast address, and it's a broadcast address. And if you need to broadcast, this is the address you need to use. And if you have all zeros in the host part, it tells you that that is a network address. There are certain range of addresses which are available for private addressing, and these are shown: 10.000 to 10.5555, 176.16 to 100 to 172.31.255.255. So that is shown in that slide, the private addresses which you can use. So let's now look at this important issue of subnets. To create a subnet address, a network administrator must borrow bits from the original host portion and designate them as subnet field. And you can see that in the diagram. So you borrow the certain number of bits from the host portion and call them a subnet field. You have to determine which part of an IP address is a network field and which part is a host field. To do that, there are a number of things you need to do. Express a subnet IP address in binary form, replace the network and subnet portion of the address with all ones, and then replace the host portion of the address with all zeros. So then you create a subnet. Now if you then do a binary AND, you can actually reverse back to get the original network address. So looking at a class B network, 16 bits for the network, 4 bits for the subnet, and 12 bits for the host. So you have borrowed, in this instance, you have borrowed 4 bits from the host part and made them all ones. Now you can then convert this, and then you then get 255.255.240. This gives you the subnet mask for this type of network. Now, Boolean operations are important when you want to do subnetting, because, like I said, you need to either end the subnet with the network in order to get the actual network address. The AND operation is like a multiplication, or it's like addition, and not changes a 1 to a 0 and a 0 to a 1. How do you perform the AND function? As an example, this is shown in this diagram. You have this address with the following subnet. You convert that into a binary form, and you get that. And this 255.255.255.0, this is what you get. If you then do the AND, if you then end that, then it results into this number, which then gives you what? The network address that you need. Now, in this slide, what you see here are the number of bits needed to create subnets, So you have an IP address, that's the default subnet mask, and this is an 8-bit subnet mask. So that's 172.16.00 for the host. The default subnet mask will be 255.255, then 0. Then the 8-bit subnet, because we've borrowed 8 bits from the host part, that also turns into what? All ones. It is this then becomes your 8-bit subnet mask, which you use for, what do you call it, finding the network address. So again, for a class B, if before subnetting the network address are that 16 bits for the network, 16 for the host. After subnetting, you borrow, in this case, about 8 bits from the host and add to the network. So you have more bits for the network. To easily remember some of the, bit patterns, this table shows you the equivalents. So if you have a 1, 0, 0, 0, 0, 0, that's a 128. If you have a 1 and a 1, that's a 192, and so on. So you don't have to commit this table to memory, but the more you work with it, you get to know it and recognize it. So how do you create a subnet? The first thing is to determine the subnet mask size. So in other words, how many bits you need to borrow. Then you have to work out the subnet mask and IP address. You then compute the number of hosts that will then be required for the subnet. So because you then have the subnet mask, then you know the number of bits remaining for the host, you can work out the number of hosts per subnet. You then do a Boolean AND operation, and then IP configuration and network diagram, such as packet tracer, and then you can do the host and subnet schemes, and then you can then determine the private addresses as well. How do you determine the subnet mask size? For class B addresses with 8 bits borrowed for the subnet, this is how it will look like. You borrow. Now, the way you determine that will be dependent on the type of network you want to build. So you get this from the design. So you go to, for example, you're designing for someone, you know that, okay, I need, let's say, on this subnet, I need 20 computers. If you need 20 hosts on a particular subnet, then of course, you don't need more than 5 bits to represent that, because 5 to the power of 5 is 32. So that gives you more than enough host addresses on that subnet, which means you can borrow all the rest and leave only 5 bits on the host part of the network, of the host. Or you can leave 5 bits on the host part. So for class C addresses, which starts around 197.15.22.131, you can have a subnet mask of, say, 255.255.234. In this case, you have 3 bits that are borrowed, and this is shown in your diagram. You have 3 bits that are borrowed here for the subnet. So in the host, you are left with 5 bits. This is what I was trying to refer to, that depending upon the number of hosts on the network, on that subnet, you then determine how many to borrow. So if you don't require more than 20, for example, then you ask yourself, how many bits do I need in order to address 20 places? Yeah? That if you took 4 bits, that would not be enough. You only get 16. However, if you took 5, you can get up to 32. So that's how you weigh it out. Right. This is an example of how to do the end operation with the subnetting, which you can work through for yourselves. How do you configure the IP on a network? Normally you do this configuration on the router. So the router will have the logical network, and it will then connect to the other physical, or to connect to the other subnets and networks. So through the router, you connect to other subnets, in the network. This table shows you some important information on subnetting schemes. So you see how the number of bits you borrow, and the number of subnets you can create, and the number of hosts that you can get per subnet. So if you borrow 2 bits, for example, from the host, it means you have 6 bits left, which you can use to provide addresses for the host on that subnet. With the 6 bits left, 2 to the power of 6 is 64, and we said 2 of those addresses must be used for loopback and broadcast. So in each case, you have to take away 2. So 64 minus 2 then gives you what? 62. So you can have a maximum of 62 this is per host. And since you borrowed 2 to add to the network, you can have 2 subnets, right? So 2 subnets. On each subnet, there are 64 hosts. So it means altogether, you can have 124 hosts in your system, in your network. Similarly, if you borrow 3 bits, then 2 to the power of 3 is 8. We reserve 2, so you left 6, so you can have 6 subnets. And then you have 5 left on the host portion. 2 to the power of 5 will be 32. Take away the 2 which is reserved, so you have 30. So 6 times 30, that gives you what? 180, meaning that you can have 180 different hosts on this your network. And the same way you can calculate for the rest of the item to see the number of bits borrowed and how many hosts you can have on the subnet and how many hosts in the network as a whole. The last column gives you the percentage utilization of the number of these things. This brings us to the end of our discussions. The topic 3, which is obtaining an IP address, I leave to you as a reading assignment, and you can discuss that further in your tutorial sessions. Thank you.